Welcome. Today, we're going to learn how telescopes work and how to calculate their resolving power and light gathering ability. We'll understand the key formulas, see what each number means, and then apply this knowledge to solve some practical NSEA problems. Diffraction limit/angular resolution. A telescope's ability to distinguish two close objects is limited by diffraction. The smaller the angular separation it can resolve, the better the telescope. The approximate formula is theta equals 1.22 times lambda divided by d. Here, theta is the angular resolution in radians, lambda is the wavelength of light in meters, d is the telescope aperture in meters. If you know the resolution you want, you can find the aperture as shown below. Convert angles in arc seconds to radians using below calculation. Light gathering power. The amount of light a telescope collects is proportional to the area of its aperture. Doubling the diameter increases light gathering by 4 times. Scaling to other wavelengths. For radio telescopes, the same formula applies, but the wavelength is much longer, so to get the same resolution, the aperture must be proportionally larger. Now that we have covered important concepts, let us apply this knowledge. Question 1. How large should the aperture of a telescope be in order to achieve a diffraction limit of 0.001 arc second for visible light of wavelength 500 nanometers? A. 2.4 meters. B. 12.6 meters. C. 126 meters. D. 24 meters. Pause the video and try to solve it on your own. We are given wavelength lambda as 500 nanometers, which equals 5 times 10 to the minus 7 meters. Next, multiply 0.001 by 4.848136 8 times 10 to the minus 6 to convert to radians, giving about 4.848136 8 times 10 to the minus 9 radians. Substitute the values to find the aperture. The computed aperture is about 125.82 meters, which rounds to about 126 meters. So the correct choice is C, 126 meters. That is enormous. A 126-meter telescope would be a giant. For visible light to reach a diffraction limit of 1,000th of an arc second, we need a truly massive aperture. Question 2. A radio telescope working at a wavelength of 1 centimeter wants the same angular resolution as an optical telescope of diameter 10 centimeters. What must be the diameter of the radio telescope? Choices: A. 2 meters, B. 2 kilometers, C. 20 kilometers, D. 200 kilometers. Pause the video and try to solve them. We have lambda radio 1 centimeter equals 0.01 meters, optical diameter 0.1 meters, and an optical wavelength 500 nanometers equals 5 times 10 to the minus 7 meters. Use the fact that angular resolution theta is proportional to lambda by d. For the two telescopes to have the same resolution, the factor 1.22 cancels, so d radio equals lambda radio divided by lambda optic times d optic. Compute the ratio and multiply by the optical diameter to get 2,000 meters or 2 kilometers. So the correct choice is B, 2 kilometers. Radio wavelengths are so much longer that to get comparable sharpness, you need a telescope that's thousands of times larger. Hence, radio astronomy usually uses interferometry to simulate extremely large apertures. Before we move on to next question, if you are finding this video helpful, please like the video and subscribe to the channel. Drop a comment too. Question 3. Venus has an equatorial radius of 6,052 kilometers. The semi-major axis of its orbit around the Sun is 0.72 astronomical units. What is the smallest diameter of the primary mirror or lens of an optical telescope required to just resolve the Venus disk during a transit of Venus? Choices: A. 200 centimeters, B. 20 centimeters, C. 10 centimeters, D. 0.25 centimeters. Pause the video and try to solve. Venus diameter is 12,104 kilometers. Distance between Earth and Venus near inferior conjunction is about 0.28 astronomical units, and 1 astronomical unit is about 149,597,870.7 kilometers. Compute the distance in kilometers. Compute the angular size theta of Venus in radians, diameter divided by distance. Substitute the values to find d. The smallest objective diameter is approximately 0.21 centimeters, which is closest to option D, 0.25 centimeters. That means even a tiny telescope, a few millimeters across, has enough resolving power to see Venus's disk during transit. The planet appears large enough on the sky during transit that diffraction is not the limiting factor for modest amateur instruments. Question 4. The pupil of the human eye is about 5 millimeters in diameter. How many times more light-gathering power does a telescope with a primary mirror of diameter about 200 millimeters, that is 20 centimeters or 8 inches, have than the human eye? Choices: A, 4 times, B, 16 times, C, 40 times, D, 1,600 times. Pause and try to solve the question. We are given the telescope mirror diameter as 20 centimeters and the human eye pupil diameter as 5 millimeters, which is 0.5 centimeters. Light gathering power is proportional to the collecting area, which goes as the square of the diameter for circular pupils. So, take the ratio of diameters and square it. The telescope collects 1,600 times more light than the human eye, so the correct choice is D, 1,600 times. That is why even a small 8-inch telescope makes many faint stars visible that are invisible to the naked eye. It collects far more light. That completes our practice questions. The key takeaway: diffraction-limited resolution depends directly on wavelength and inversely on aperture, so shorter wavelengths and larger apertures give better resolution. Check out our playlists for more videos on NSEA questions, and please subscribe.